Hello everyone. In today's lesson, we will learn about how to solve simultaneous equations with matrices. So by the end of the lesson, you will learn how to solve systems of linear equations with a method called matrix inversion. There is also another method called the Cramer's rule, but just for the purposes of demonstration, we would like to simply see how we can apply our coding skills to real class problems. So this is an example of a system of linear equations. So we have three equations, and then we also have three unknowns. So this is what usually in mathematics would be called three equations with three unknowns. The unknowns are the variables x, y, and z, whose solution we seek from this system of linear equations. Generally, systems of linear equations can be expressed in matrix form as Ax equals b, where A is the matrix of coefficients, X is the matrix of variables, and B is the matrix of constants. So we would use the colors to be able to differentiate between these matrices that we are going to describe. So you would notice that the coefficients are colored red, then the variables black color, and the constants blue color. So given this system of linear equations, we can create the matrices in order to express that form as, so we have the matrix of coefficients, the matrix of variables, and that also equals the matrix of constants. So we will notice that the matrix of coefficients multiply the matrix of variables, and that is the very matrix form that we just mentioned earlier as representing the systems of linear equations. So if you want to solve the variables by matrix inversion, then the Ax equals b, you will do some mechanics. This is normally taught in class, where you pre-multiply both sides of the equation by the inverse of a matrix. And the inverse of matrix A multiplied by A gives you an identity, and that simply equals the same matrix of variables x. So in the end, this is just simply the solution to the systems of linear equations, and we can get the values for x, y, z, which are the unknowns in the system of equations that we have just shown before. So at this point, let's go to R and learn how to solve systems of linear equations by matrix inversion using code. Now in R, we do have our system of linear equations over here, and we have the matrix form Ax equals b. A is the matrix of coefficients, x is the matrix of variables, and b is simply the matrix of constant. So all we want to do is, if you actually want to solve the matrix of variable x, just as we showed in the slide, x is simply going to be equal to the inverse of the matrix A multiplied by the matrix of constant b. So all we have to do is just create the matrix of coefficients. So let's simply call it A, just like we represented in the matrix form. So A and then matrix data equals, now let's pass the vector of values, which are going to simply be the coefficients. So for the very first line, we do have 7 minus 3, 6. Okay, so that is 7 minus 3 and 6. Then 5, negative 2. So let's proceed with that. 5, negative 2, and 2 for the second line. And the third line, we have the coefficient to be 2, negative 3, and 8. Once we are done, we can now specify the number of rows to be 3. And we know that the number of columns definitely will also be 3 because there are 9 elements passed to the data argument. So R figures out, if you specify the number of rows to be 3, it knows that the number of columns should also be 3. But you would see that we wrote these numbers according to how they were arranged by each line of the equation. So we want these to be arranged by rows, not by columns. And therefore, we simply have to specify the by row equals true. So I intentionally did it that way. If you didn't want to specify the by row equals true and simply maintain the false, which is by default, then you could have written these numbers in this very order: 7, 5, 2, minus 3, minus 2, minus 3, in that very order, column wise. But we actually did it by row, so we just simply specify by row equals true. And we can go ahead and execute this code. Now we need to also write the matrix of constants. And so data equals, the constant is just simply 5, 11, and 10. And that also has to be 3 by 1 matrix. So I would simply have my vector of 5, 11, and 10, and then I would specify the number of rows to be 3. I may decide not to actually specify the number of columns because that is also 1 by default, and there are 3 elements, so that will fit very well. So let's go ahead and execute this B code, this B matrix. Now let's print them to the console. So this is the matrix of coefficients, all right? And then this is also the matrix of constants. And so once they are in the very form that we are looking at, we now need to solve this system of linear equations. And by matrix inversion, we just have to multiply the inverse of matrix A by the matrix B. And it's very simple. We use the solve function to find the inverse of a matrix. So I just put in matrix A into the solve function. Then we use the matrix multiplication operator, percentage asterisk percentage, and multiply by the matrix B. Actually, there was no need for us to create the matrix of variables because we're only seeking the solution for the system of linear equations, and this is what we can actually do. So in which case, if I execute this code, we end up getting this to be the result. Perhaps in class, you may have been required to actually leave this in fraction form, but in R, we only get the decimal places, so we are simply cool with that. Also, you would have observed that the dimension for this inverse of matrix A and that of B are conformable for multiplication. That is how come we got this very result. So, for example, let me clear the console and just demonstrate this within a few minutes. So we have dim solve A, which is just simply 3 by 3, and then we have the dimension of B also to be 3 by 1. So we notice that the number of columns in the inverse of A equals the number of rows in the matrix B, and that is how come they are conformable for multiplication, and hence we were able to get the result when we went ahead and execute this code. But if we had turned this the other way round by saying B and then multiply solve A, then we are going to get error because they are not conformable, because if you turn it the other way around, you'd observe that the number of columns in B is not equal to the number of rows in A, and hence this will not be conformable for multiplication.